Okay, so little introduction. I'm Travis Justice. I am a fourth year student studying life science and chemistry education. So I'm going to be a high school science teacher. Um, and sorry, I'm filming in my bedroom, but it's the only quiet space I have right now. um, but for this paper, I studied two molecules, both from the American Chemical Society Molecule of the Week. So I chose uric acid and 1H123 triazole, just because both of those are pretty interesting and they have a lot of uses in the medical field. So I kind of wanted to research something that had uses in our everyday lives and not just some organic molecule that people study just for the heck of it. Um, so uric acid, um, I thought was more interesting out of the two, just because it's something that we hear of a lot, but we don't really know what it is. So uric acid was discovered in 1776 by Swedish chemist Carl Wilhelm Scheele. So he was studying human urine and kidney stones. Not my preferred area of study, but whatever floats your boat, I guess. So during his studies, he found uric acid in urine. So this is a byproduct of foods we eat. So uh, foods we eat that are high in purines. So purines are broken down in the body and changed into uric acid. So foods that are high in purines are seafoods, red meats, organ meats. So if you're eating livers or kidneys, high fructose corn syrup, and alcohol, especially beer. So an enzyme, xanthine oxidase, digests the purines in these foods through a redox reaction, and it oxidizes the purines. So a product of that reaction is the uric acid. So uric acid is mostly dissolved in the blood and filtered by the kidneys and released in urine. So we don't really have any issues with it in the body. But excess amounts by eating those foods listed can result in gout, also known as hyperuricemia. That's the medical term. So I've heard of gout a lot, but I never really knew what it was until I did this research. So it's literally crystallized uric acid in your joints, specifically those in your feet, because it accumulates down there, and it can cause excruciating pain and discomfort and difficulty walking if not treated correctly or prevented by diet. Um, and so here is a drawing of uric acid. So we have two cyclic structures, and it's fairly simple overall compared to some of the things you can see, especially biological. So it was pretty easy to draw, thankfully. Um, and so my next molecule was 1H123 triazole. So this was synthesized by German chemists Otto Dimroth and Gustav Fester. So they heated a solution of hydrochloric acid and acetylene at 100 degrees Celsius for 70 hours. Um, so most of the isomers that they found and are still in existence have very similar boiling and melting points, so it's very hard to separate them, if not impossible. So it's very tricky to get specific isomers of the triazoles. And then the most common reactions that triazoles go through organically are electrophilic substitutions, alkylization, and bromination. Its most common reaction is with bromine because it's very easily brominated. Um, and like I said, both of these have uses in the medical field. So one 1H123 triazole is used in an antibiotic called tazobactam, and what it does is it helps that antibiotic treat different kinds of infections. So it increases the number of bacteria that are affected by it. So here is the structure of 1H123 triazole. It's very interesting because every triazole has the three nitrogens and the two double bonds. So it's not something that we see very common, three nitrogens right in a row in molecules. Um, and it's, like I said, the isomers of it, all of them will have this structure right here, but they're so similar, it's just very hard to separate them. And then this is the antibiotic tazobactam. So you can see the triazole right here attached to the end, and then this is the antibiotic. So with the addition of the triazole, that lets it treat more types of bacteria. Thank you.